Hello everyone. Today we're going to be talking about forward kinematics, and this is the subject of Robotic Systems Chapter 5, and specifically these readings here are the ones that you should pay the most attention to. So when we talk about articulated robots, we usually mean that we have a robot that's mostly a rigid structure connected by joints. It also has geometric CAD models describing the geometry of the robot links attached to those reference frames. And a configuration of the robot is a way to specify the whole position of the robot, and it usually consists of a set of joint angles. And the process of converting from those joint angles to the placement of the reference frames of the links is called forward kinematics. There's lots of different types of kinematic types of robots, including serial robots, which have a fixed base, and then they have a sequence of joints leading up to some tip. And then there are also branched robots that have multiple branches, such as the human body or an anthropomorphic hand. But in any case, we can model these using a common set of kinematic conventions. So the process of forward kinematics takes in a description of the robot's kinematics as input, and it also takes in a configuration, and then it tries to produce link frames relative to the world frame for that given configuration. The kinematic description consists of the reference frame of the robot. This is also known as the zero position. It is also given the robot topology, so which joints are connecting which links together, and also the joint types and also their axes. So for example, if you have a revolute joint, it will give you the axis in which the joint is rotating, and if it's a prismatic joint, which means it's translational, it will give you the axis along which that link translates. So we're going to go through some derivation of how to calculate forward kinematics. A bit of a note on notation is that we are going to imagine that the transforms that we're working with are just going to be homogeneous coordinates so that they're d+1 square matrices, d+1 dimensional square matrices. And you have to also remember that composition is going from the right to the left. So if you think about the sequence of application of the transforms, read the sequence of multiplications from the right to the left. Now with that, let's try to derive how to perform forward kinematics. Let's start with a simple two-dimensional example. Here, this is the reference frame of a given robot. And for the reference frame, each of the links is going to have defined its own reference transform. This is going to be denoted T sub I comma ref for the ith link. And they're going to be defined for each of the links of the robot. Now let's see what happens when we rotate the first joint. Let's suppose that T1 ref is translated L0 distance along the x-axis and it's rotated somewhat. Now, if we're to then rotate about this axis, this joint axis, we're rotating about the point L0, 0, and we're rotating Q1 units, radians in that direction, and then along that axis. So the final transform we want to get looks something like this, and we derive it from composing the reference transform with that local rotation about Q1. Keep in mind that T1 is converting from link 1's local coordinates to world coordinates. And so that first rotation is just rotating about the link's local coordinates because by convention, we're going to set up all of the reference frames such that they have their origin at the link axis. Okay, so next, let's look at the second joint. So let's start out by assuming that there is no rotation for that second joint just yet. And so the transform of link 2 after Q1 has rotated is in this position here, position orientation here. So this is just a function of Q1, but there's some offset here that is converting from the coordinates of Q2 of link 2 into the coordinates of the world frame. So if we want to think about this, we're taking points that are defined in the local coordinate system of link 2 to the world. So we're going to transform those from the reference frame into the world. Then we're going to transform them into the reference frame of Q1, giving us a point that's expressed with respect to the first joint. Then we'll perform that rotation and that final reference transform, and then we'll get the transform of link 2 before we rotate link 2. And we'll call that T2 no rotate. Now, finally, let's perform that rotation for joint 2. And it turns out that since this is happening in the local frame of link 2, and we've also taken the reference coordinate system to have its origin about the joint axis, it's just simply a two-dimensional rotation about the origin with angle Q2. And this is the final expression here. You can start to see that there's a bit of a recursive nature happening here, and we're going to express the final formula using exactly this. So the transform of link K as a function of the joint angles from 1 to K is equal to the transform of link K minus 1 times the reference transform from link I to link I minus 1 times the local rotation about Qi. We can also express this as a product formula looking like this, where the terms are written out from the left to the right. So the way that this works is that we basically are going from the root of the robot down to its tip, and so we'll calculate first T1 of Q1, T2 of Q1 and Q2, T3 of Q1 through 3, and then finally T4 of Q1 through Q4. So as an example, if we wanted to calculate the forward kinematics of a two-joint arm that has a reference system given by essentially just a movement along the x-axis to get to the first frame, and then another movement along the x-axis to get to the second frame by lengths L0 and L1 respectively, then what we can do is calculate these terms here and express the rotation matrices with this type of homogeneous transform matrix here, where Ci is a shorthand for cosine of Qi and Si is sine of Qi. And if we just go and calculate this whole thing out using symbols in the place of these matrix entries, then we can see that T1 is going to be this matrix here, which has a rotation about Q1, and it also has this translation of L0 in the upper right corner. Now to calculate T2, we'll take T1, like we calculated before, and then T2 ref superscript 1 ref times RQ2, and that is that second matrix here. And if we just go ahead and mechanically multiply all these things out, we see that there's, in the upper 2x2 rotation component, there's a bunch of sines and cosines, and it simplifies to the basically terms that depend on the cosine of Q1 plus Q2 and the sine of Q1 plus Q2. And the translation is going to be L0 plus C1 L1 as the x component, and then L0 plus S1 L1 as the y component. So with this type of expression, we can generalize this to tree structures. This kind of serial robot formula only works when basically you have a serial robot. And instead, we're going to define something known as the topological sort, where the parent of link K is given by P of K. And the reference transforms that we're going to be looking at are going to be the transforms from the link's reference system to its parent. Now, we can also define the list of ancestors of a given link. And with this definition, we have a very similar expression to what we had before. Basically, the transform of link K is a composition of relative transforms between reference coordinate systems times rotations, but only going from the root link up to the link that we're considering, and we're only following that chain up to that root link. So for example, if we want to calculate this for a hand of a humanoid, I will look from the body to the different arm links up to the hand. Now, this was all expressed in 2D, and in 3D, actually, everything is more or less the same. The main difference is that the joint axes have to be actually defined, and they are typically defined relative to the link's reference coordinate frame. All right, so certain joints will rotate about the z-axis, certain joints will rotate about the x-axis, and I need to specify this as part of the kinematic definition. And to get the rotation matrix, we will use axis angle parameterization, so we're always rotating about the origin about some local joint axis by that angle Q1. Okay, but otherwise this expression is pretty much the same as before. There are also generalizations of this beyond revolute joints to prismatic joints, screw joints, and other types of more exotic type of joints, including free-floating bases, which can be expressed as a set of translations and rotations as Euler angles. Just as a summary of what we have for forward kinematics, we'll have a articulated robot, which can either be a serial chain or it can also be a branched tree. It's defined by some number of links, parent indices for each of these links. If you want to denote that the link is attached to the world frame, the parent will be nil. We will have transforms from the link to the parent at the reference configuration. We may also have joint limits. We'll also have indicators of what type of joint we're talking about, for example, revolute versus prismatic, and we'll also have the axis of rotation or translation expressed in the local coordinates of that link. Now, from all that information and the robot's configuration, the configuration is going to be changing much more frequently than the kinematic structure, we're going to be able to use a one-pass algorithm to calculate all of the link transforms. And essentially, an efficient algorithm looks like this. It's an order n algorithm. We start by going from the first link to the nth link. We're also assuming that the indices are topologically sorted so that the parent of each link comes before it in this order. With this, if the parent of a link is nil, then we just calculate the multiplication of the reference transform times the link's local transform. Otherwise, we compose the parent's transform with the reference relative transform times the local transform. And that's it. Very simple algorithm. The trick here is that this TI to TI reference is going to be the local transform of that link, and it's going to depend on the joint type and also its axis. Just to complete the expression of each of these algorithms, revolute joints are given by this local transform, prismatic joints are given by this local transform, and we can also express more exotic type joints like screw joints using a sort of combination of the two. Now, when we talk about robot kinematic definition files, one thing that you'll often see in older textbooks especially is Denavit-Hartenberg Convention. It's a very compact representation of serial robots' reference transforms and their axes. It reduces the number of parameters that you need to specify the reference frames of a robot down to 4 parameters per link. Now, it's not used very often nowadays, and I also don't prefer it because it oftentimes makes you choose very nonsensical conventions for your robot, but you should be aware that it exists because some robot manufacturers will still use DH convention. Now, the more modern approach to kinematic definitions is using some robot kinematic definition files. And the most popular is called URDF, or Universal Robot Description Format. It's an XML-based format. It has a structure that looks something like this. You'll define a set of links, you'll define a set of joints, and they'll have various parameters that go along with them. Now, in the clamp system, we can either read URDF, or we also have a more compact format called the ROB file format. It's much less verbose, and you can see here in 22 lines we have a complete robot defined, whereas XML, the URDF in XML uses over 100 lines. So as a recap, forward kinematics goes from a configuration, which is a set of joint angles, to link transforms. It requires a robot kinematic definition, including reference transforms, joint types, and joint axes. There's a fast order n algorithm to calculate forward kinematics, and in clamp this is done essentially automatically every time that you call robot.setConfig. There's also different types of robot kinematic definition files, and these include not just kinematic information, but also information about the robot's geometry, mass information, etc. And clamp can read both URDF and ROB file formats. That's it for today. I'll see you next time.